Welcome to Lecture 4. In this series of lectures, we will discuss Chapter 3, What is Earth Made of? Introducing Minerals and the Nature of Rocks. This lecture will be broken up into 3 parts. In the first part, we discuss mineral definition and formation. Part 2, we discuss mineral properties and identification. And in Part 3, we discuss minerals as gems and in rocks. On the left-hand side of your title slide, we have red quartz, which is colored red by the trace amounts of iron oxide, also known as FeO, in the quartz. So, what is a mineral? Well, minerals have a very specific definition that includes 5 characteristics. The first being that all minerals are naturally occurring. This means that minerals were not created by humans in a laboratory, which is known as a synthetic material. Minerals are also homogeneous in composition and structure. This means that every type of every quartz mineral on Earth, it has the same composition and structure. This can vary somewhat because in nature it's never perfect, but in general, throughout quartz minerals across Earth, it has the same composition and general chemical structure. Third, minerals have to be crystalline solids. This means they have to be solids at Earth's ambient temperatures, and they have a very specific to their mineral group, a form or habit. Fourth, minerals have a definable chemical composition. So every mineral everywhere on Earth has a defined chemical composition, plus or minus some impurities. And finally, minerals are inorganic, meaning they are not formed from living material. So the mineral on the left is called malachite, and it often is formed with copper, and it's a nice, pretty greenish color. And it has all of these characteristics. Any piece of malachite all across the world, you will find it is inorganic, has a definable composition, is crystalline solid, has a homogeneous composition and structure, and is naturally occurring. So let's go back to our example of quartz. This is a great example to explain to you each properties of a mineral. So quartz occurs in nature. It's not made in a synthetic process by humans. For example, you find most beach sand that you typically think of as being white or tan colored is made up of quartz, and this occurs naturally. Quartz has a homogeneous composition and structure. Again, could be altered with impurities as shown in the picture on your left. So we have, in both photos, we have quartz crystals, but the red quartz has slightly more iron in it, whereas the clear translucent quartz has no iron. Quartz is a crystalline solid. You notice in the pictures that these are both solid materials. Quartz has a definable chemical formula with the chemical formula of SiO4, which creates something called the silicate tetrahedron, meaning that one silicon atom is surrounded by 4 oxygen atoms. And this is true in every quartz crystal and a crystal structure that comes from a regular arrangement of the atoms in the mineral. It's important that we understand that crystal structure is defined by atomic structure. So the larger scale or macro scale mineral that we can see with our naked eye is its form or habit is created by the atomic scale relationships. And finally, quartz is inorganic. One thing about minerals is that some minerals can be created as a product of living things, but in order to be a mineral, the product has to not be living itself. So let's take an opposite example. Why is glass not a mineral? Well, glass is an inorganic solid with the same chemical formula as quartz, which is either SiO2 or SiO4, depending on how you define the quartz crystal. But glass does not have a crystal structure, and it is synthetic, meaning it's made by humans. The crystal structure, or the lack of a crystal structure, is important because the way that glass forms is that you heat up enough quartz crystals for that they fuse together in an oven. And this fusion of quartz grains allows for the disintegration of any particular crystal structure. Rather, in glass, you have a random arrangement of atoms, or a non-orderly arrangement of atoms. So, as mentioned before, crystal structures produce distinct crystal forms or habits. And also, mineraloids do not have crystal structures, but have all the other characteristics of minerals. So I would ask you if you can think of some mineraloids. The two photos on the bottom right are mineraloids. So glass is not a mineraloid because it is synthetic, but on the black mineraloid on the right side of your screen, this is called volcanic glass or obsidian, which is distinct from human-made glass. And this is a mineraloid because it has all of the characteristics of a mineral, except it lacks a crystal structure. The reason for this is that as it explodes out of a volcano, it cools too quickly for atoms to arrange themselves in an orderly fashion. The bottom right picture is of something called amber, which is fossilized tree sap, and a mosquito is trapped in this amber as a fossil. Some of you may know, as a pop culture reference, that in Jurassic Park, the DNA that was extracted to create the dinosaurs was extracted from a mosquito trapped in amber who had bitten a dinosaur. While this is science fiction, it is not too far off from the truth in terms of how we can determine ancient DNA structures. In the middle part of your screen, you have different crystal structures for minerals like halite or table salt, diamonds, quartz, and calcite, and garnet, to name a few common ones. Next, we'll discuss how do minerals form. Later, we'll realize that each of these processes occur in the formation of a rock, as rocks are aggregates of minerals. But for now, let's just discuss minerals. One method of formation is through solidification of a melt. So as a melt or liquid or partially liquid or molten rock is exploded at Earth's surface through a volcano or is cooling in a magma chamber, minerals form through solidification. And the way that this happens is that they form one by one, crystallizing out of the melt. So here we have a picture of the process. Another way of formation is through precipitation from a volcanic gas. So precipitation of minerals from volcanic gases can also occur. For example, yellow sulfur crystals form on this way in and around volcanic areas. Here we have a geologist sampling some sulfur. Looks rather dangerous. Third, we have precipitation from a liquid solution. While the first two examples formed in igneous environments, this third example is a sedimentary type of mineral formation. So precipitation, when we think of it in typical speech as non-geoscientists, we think of rain, but precipitation can mean any object that is falling through another medium. So when we have precipitations of solids or minerals, as water evaporates or through water, then we have the creation of some minerals. One example is As water evaporates, salt crystals get deposited on lake beds. This is particularly true in mountainous environments and arid environments. A fourth example of how minerals form is through diffusion in solids. This is actually happening in solid rocks as they undergo changes in heat and pressure that result in something called metamorphism. So this diffusion is actually the movement of atoms migrating through the crystal lattice within the rock. So this can form things like garnets, minerals in metamorphic rocks from non-garnet minerals. This is a difficult process to visualize because we can't see it in real time. This happens deep within the earth. A fifth process is called biomineralization. This is also a sedimentary process. So this refers to the production of minerals by living organisms. And one example is that reef organisms extract ions from marine environments, from the water, to make their shells. And so any sort of mollusk shell is created through this aspect. Eventually, as those organisms die, whether they're large organisms like mollusks or crabs, or whether they're planktonic animals, their shells fall through the water column and get deposited on the seafloor and eventually end up in things we call sedimentary rocks. What's important is that in every process, crystals grow as more ions attach themselves to a structure. So if the crystals have more space to grow and more time, they will eventually grow larger and fill that space.